Professor Moritz Bigalke. Moritz Bigalke is Professor for Soil Mineralogy and Soil Chemistry at the Technical University of Darmstadt in Germany. His research focuses on the biogeochemistry of contaminants in soil to contribute towards the preservation of essential soil functions. He primarily investigates the fate of trace metals and plastic particles of macro, micro, and nano size within the soil system, their interaction with the soil solution, and their uptake by plants. Professor Bigalke will discuss about the effect of different steps needed to analyze microplastic, such as sampling, extraction techniques, data analysis, and so on, and the effect on the monitoring and quantification of these steps of analysis of microplastic. His keynote is entitled 100 to 10,000 microplastics per kilogram. What are the problems with analyzing microplastic concentrations in soils? Moritz, the chair is yours.
Thanks a lot. Thanks a lot for inviting me, and thanks a lot for introducing me. It's a pleasure. I hope you can hear me well. I tested another microphone. It seems to work. Perfect. Yeah, the topic I want to talk about is just something we already heard quite, even if the conference is not lasting too long until now, we heard it already several times, that there are certain problems in analyzing or getting microplastic concentration in soil. And already yesterday, with the introduction talk, there was the wish to get real concentrations. So this is what we are, at the moment, we are still facing problems to really analyze reliable and get comparable data for microplastic concentration in soil, but also in other environments. So I think soil is the most complicated at the moment. And this is what I want to talk to you about today. And it's not complete. I mean, it's quite a huge topic. I will focus more on certain aspects which I thought are not discussed too much in the literature by now. Yeah, the background is when you look about microplastic concentration in soils, you can have a look at this review, which was published 2020, and they say you have about 30,000 particles per kilogram up to this concentration, and if you have more, and then they did this nice overview graph. They have different land uses here, from agriculture, horticulture, grasslands, fallow, forest, and other sites, which are mostly industrial and urban sites. And then on the other axis, you have the logarithmic scale of the plastic counts in the soil. And then you can see here for the agriculture soil, at the very left, you can see that there's a huge spread in the concentration. So it reached from no plastic at all up to nearly 1 million plastic pieces per kilogram. And then, I mean, you can assume that might be the truth. It might be that just some soils are not contaminated and others are heavily contaminated with plastic, and then you get the spread. But sometimes if you look on the data for certain studies, for example, there's one published 2021 about agricultural surface soils in Shanghai suburbs. So I would assume this is a high population density area, and in China there are a lot of foils used. So I would assume it's rather high input, but what they found is something about 80 particles per kilogram. No? And then if you look at other sites, what is recently published for agriculture use floodplain soil in Germany, in the same surface soil up to 50,000 particles per kilogram, and in the lower soils even more than that, up to 85,000, I think. And of course, they say it's a lot from the river, from the floodplain, but still you see that there's not a small difference in concentration, but these are really different orders of magnitude what we are talking about. So the question is really if this is these values which are reported, if this variation comes from the real variation in concentration in soil, but or how much of the variation depends on the analytical methods used. So when we talk about microplastics, so it's a quite simple thing, or it's a synthetic polymer of a certain size. This is what you all know about, and also of course the question why is it so complicated to analyze it. We have the capabilities to analyze a lot of very trace chemicals like pesticides, or we can analyze them to nanogram per liter concentration, so very sophisticated analysis, and we can do it quite now quite well until now. So what's the problem with analyzing microplastic? I mean, I think the biggest problem is that we are really working with particles. And particles have some complications in the analysis compared to other substances, so you cannot, or at least what we not do is to dissolve them or something to get a homogeneous distribution, but we want to analyze the individual particle. And especially for soils, we have the problem that, of course, we analyze particles in a matrix of a lot of particles. So it means even if you have high microplastic concentration in soils, then you have might be one microplastic particle, and then you have thousands or millions of natural soil particles around it. So it's quite hard. And all the soil particles is, of course, quite diverse. Can be very different particles. Can be silicate minerals. Can be iron oxides. Can be organic matter. Can be organisms. So it can be everything. And what we need to do is that we find out polymers just by its specific properties or composition. And this is quite challenging, especially because microplastics are, of course, carbon-based polymers, and we have a lot of carbon-based substances in the soil, which are also sometimes very close to the synthetic polymers, natural polymers. So the first thing is that we work in matrix, which is quite complex. And the second one is, of course, that also the microplastic itself are quite complex. So this is just one sample where we extracted microplastic from a very polluted roadside soil. And it's not, it's an old version of the method we are using now. It's not a very clean filter, but it's a filter which I always use because it's so full of plastic, and you can see the whole variability of plastics here. Because on the one hand, it's what the people throw out of the car window, so just waste. And on the other hand, you have a lot of tire wear in it. And if you now look on some certain particles, you might think that they of course have different shapes, what we already discussed about. So they have different polymeric composition, and they have different sizes, of course. So these are now the biggest one I show you because you can see it, but it's clear that we have also particles going in the lower micrometer or even nanometer area. And then they have quite different properties. For example, the density, which is quite important for the extraction methods we are using, they are quite different in the densities. And of course, also the different chemical properties. The chemical properties, the chemical stability is very different, and then all these properties also change upon aging of the plastic. So if the plastic stays in the soil for decades, then of course the surface changes and also the chemical properties change. This is part of the complication. To talk now about the analysis, it's mostly focused on certain aspects of the analysis that I want to go now through more cascade of analyzing steps for microplastic. So this is the analytical process, so the whole thing, what you do from the problem definition until you reach your results you can discuss. And I want to talk about today about the sampling, the sample processing, analytical sample preparation, and real measurement and the data evaluation, which is quite critical, I think. So when we talk about sampling, we have again the problem that we are working with particles. And these particles can be different distributed on the site. It's not like when you have, for example, metal contamination, then you have a base concentration of metals everywhere, but the particles can really spread a lot. And what you see here is just two plots from a review or a study from Ju and Fleury, where they just assumed certain microplastic concentrations in soils and calculated how much sample you have to take to get a representative sample of a certain site. And what you can see here is the concentration on the x-axis. So you start with 10 particles up to 10 by the power of 6. And then on the other hand, on the y-axis, you can see how much samples, how much sample volume you would need to sample. And then you see it's two figures. The one is for homogeneous distribution at the site, and the other one is for cluster distribution. So a homogeneous distribution, you can just think you have particles which are homogeneously distributed at the site. In the cluster distribution, you can assume if you have, for example, bigger plastic particles which fell down and then they decomposed to smaller particles, and then you would think you had a big particle at the beginning, then you have a cluster of small particles. And of course, these are important things to think about. So how is the distribution, homogeneous, clustered? and how many particles I assume. This is, of course, the more you have, the smaller the samples has to be you have to take. But then there's also a question about the size of the particles, for example, which needs to be into consideration, and the specific shape of the study site you have. All this is now just for a plain area, so it's even rather underestimation. If you have a complex topography or something, it might be even more samples you have to take. Yeah, and you can see here that the lower the concentrations in the sample volume you have to take gets dramatically high, so you cannot do it basically. But then if the concentration gets more to what we expect now to be real, then the plots go down here. You can see a zoom in. So it's less good to see, but it's still quite some samples you have to take. And this is now an assumption for particle concentration of 10,000 particles per square meter and a cluster distribution, and then they compared here. So from this graph, you can see basically that you would need 2 square meters of soil to sample to get a good sample. And what they do then is that they still compare if you do this volume in just 2 boxes by 1 square meter up to nearly 1,600 cores of 4 centimeter diameter. This would all be the same volume. And then you can see how your measured concentration would behave according to the model. So this is one aspect you have to keep in mind to get a real representative sample. It depends a lot on the microplastic concentration, the distribution, and the site properties, and you would still need quite a huge amount of soil to be sampled and quite a huge amount of effort to get a representative sample. And this means in terms of comparability of the results at the end, that of course only if you have a representative sample you will get 2 times the same result at the end. Next one is sample processing, so I don't have very sophisticated slides here. I couldn't find a nice picture, so I gave you this. You might not know what it is, but I always use it in lecture. So I just have a plastic bag full of soil, and then I put in this silver pearls, which are quite light, or about the density of plastic. And then I mix them very well, so you don't see it, but then I shake it, and you can see that they just move up. Or that means it illustrates just the problem of demixing of samples. So you have to imagine if you take a sample which is 2 square meters or something, and then you have to handle it somehow, or even if you reduce it, you homogenize and reduce it, you have the problem that it's always demixing because you have just some components in the soil which are very heavy, like iron oxides, which have a density of 5, and then you have plastic which has a density of 1. That means if you carry them around in the bag, they will just demix, and the plastic will go to the top, and the other parts will go to the bottom. And this is a real problem for plastic because the density is so different from soil. You really have to take a lot of effort in taking subsamples of a sample. So homogenizing the sample is very important, and then also the sample splitting into subsamples. So this is also, it's hard to quantify the errors you introduce there, but it's quite likely that you can introduce a huge error there. So now we come to the extraction. This was something which was already discussed in previous talks this morning. Extraction method was shown, and there you have quite a lot of different methods. And the aim is, of course, that you separate the plastics you want to analyze from the soil matrix, or because otherwise you will never see them. And there, as I said before, the problem is that the properties might be very similar, for example, between organic matter and the plastic. And so you have to find a compromise in cleaning up the plastics, but removing other particles. And there are quite different approaches used. One is that you use an oil to separate the hydrophobic plastic from the not hydrophobic soil components. This is used by some groups. The most used one is the density separation we heard already about today, and which is used in the most methods, but also there's quite a difference in the density which is used, which from 1, so from water, until to 1.8 about zinc chloride or sodium iodide. And then normally this density separation, which you can use to really separate the minerals from the plastics, there are digestion steps to separate the organic matter from the plastic. And then there are sometimes more sophisticated methods use pre-digestion steps with enzymes, for example, or with other chemicals, and then finally the organic matter which is pre-digested is then oxidized by Fenton reagent, hydrogen peroxide. So, and also there, of course, is a potential for generating different results just because you clean up the sample in a different way or you use different densities in the sample. And then there are also other steps like filtration, different mesh sizes, which might influence your results. Just for an example, which is one of the, I think, most sophisticated methods which is used by now in Bayreuth, where they just sieve the sample and then everything above 500 microns they analyze manually, more or less, and then you have this automated method where they also have the density separation, and then they have a huge bunch of enzyme steps and oxidation steps, which I think it takes alone until 8 days, something like this. And you do a second density separation, then you do the analysis. So you see, there's no standardized method, as you might have heard a lot of times before. So variations in these individual steps might also have influence on the results. This is the method we are now using in Minagris. We have implemented there. In principle, it's similar. That we separate particles bigger than 2 millimeter to analyze manually, and then we also have first the density separation step. Then we do a pre-digestion of these enzymes, but with urea, thiourea, which we freeze, and it breaks organic structures. Then we do an oxidation step, and a second density separation step, and then finally we analyze it. So it's quite similar. And of course, what all the methods do, we have seen it in the morning, so we also did the quantification of the recovery, and also the other methods do it, but still the results can be quite different depending on the properties of the plastics in the soil. And finally, what you get is this kind of filter, which is mostly analyzed then for the microplastic. So if you go now from the extraction to the analysis, then of course you have this filter. It's the easiest step, which was done in the past a lot, is just microscopy and then manual identification. Sometimes you use other tests like hot needle test to identify the plastic. But it's clear that if you want to analyze something like this in the microscope, just on the one hand, it takes a lot of time and a lot of expert knowledge. So it's must not be very comparable depending on the person doing it. And you cannot go to the small particles because they're just very hard to recognize as plastic or to differentiate from other particles. So what people do most is the micro-FTIR, where you have, for example, your filter, photograph, and then you can analyze different particles which are colored here, and then you get the spectra. And you take the spectra and compare them to a library, and then if you get a good fit to a polymer spectra, to a plastic spectra, then you assume that you identify a microplastic, or this how it basically works. And what we did now in the Minagris project, so the Minagris project is this project to analyze microplastics in agriculture sites, and not only the occurrence but also the consequences. But when we started the project and we compared different methods to see to get our methods comparable, which were already existing in the project, and to see the quality of what we did. And then we used we tested different instruments. The one was an FTIR, so micro-FTIR, but with a single element detector, so an MCT detector. And what you do there is that you generate the optical images of your plastic, and then they are recognized automatically and measured one by one. And what you get then is a spectra of the single particle, and you get the shape and the size from the optical image. Second thing we did is this FPA FTIR, that is a multi-element detector where you get about 4,000 spectra in one measurement. And with this you can really analyze each pixel of your filter. So you get not like here from the optical image, but you get really a hyperspectral image where you can analyze each individual pixel of the filter for is it plastic or not. Another method is a laser direct infrared analyzer, which you can see here, where you have, instead of this FTIR, you have a quantum cascade laser which hits your particle, and then you get the reflected radiation. And you can also analyze it as an infrared spectra, but it has a much narrower range than the FTIR. And the fourth method we're analyzing is the Raman microscope, where also an optical image is generated, and then you shoot with a laser on a single particle and get a Raman spectra out. And we analyzed, or we compared this 4 different methods. For the Raman microscope, we saw a lot of fluorescence problems because of the method, so we excluded it from the quite from the beginning. And what you get when you compare the different values here is that you can see it's quite different. Or we have 3 different soils we analyzed, one from Switzerland, Spain, and Netherlands. From our case study sites, and you get concentration range here, and this is not logarithmic this time, and then you get concentrations here. You always get here, for example, MCT is a single element detector, and you have 3 different values here, 3 different thresholds. It's just how well you want to fit the spectral measure to the library you have. The higher the value, the higher the requirements you set for plastic to be recognized as a plastic. Means the higher the threshold you set, the lower the concentration. And so we have single element detector, multi-element detector, and the laser direct infrared. The laser direct infrared we just have for the Spain and Netherlands side. And now you see here in red is what is reported in the Brooks et al. Study from this review at the beginning. Then this is another study where they found higher concentration of floodplain soil, and then you see our initial values, and you can see that we are quite high already with the single element detector, and for the multi-element detector we sometimes get very high values. For the laser direct infrared also quite high value. And then of course you have to look into the reasons for that. And one problem, for example, we encountered that with this FPA detector, not the whole particle is recognized as one particle, but it can be that only parts of it, because really every single is measured, and then the software has to generate out of this, has to generate a particle. And when you measure one particle, then the spectrum might change because the shape of the particle, you have different thickness of the particles, so you get different spectra. So for the software, it's quite hard to identify one particle really as one particle, and you might get several particles measured out of one particle. And this is something we really have to approach now, for example, with manual correction issues to get the values corrected. And there are other issues, of course, or other things you have to control. Control the spectra maybe manually to see if they really fit well. So we really have to invest now in this comparison to get the values, or in this manual work to get the values very comparable. And this would be something for the composition. You can see here is a single element detector. You always get the most polyethylene, but then also other plastic and a bunch of other things. And then you see here is a single element detector. You get variability, which is much lower with the FPA and the LDR. But I think this is mostly because this other method, just at the moment, have generated much higher values, and then the PE is just estimated too high, and it's overprinting the other thing. So there we are still working on it at the moment to get really the values down, but we can also compare it a bit to what is published in the literature about this problem of the data evaluation, which is, I think, quite a critical one. So this is a study which was published this year with water samples, and they analyzed data sets, so real finished data sets with 2 different programs. One is the Biot particle finder on the top, and the other one is the simple model, simple software on the bottom. And here are 2 data sets, which are just 2 different sample collections, more or less. Then you can, and they did the first comparison, then you see that here with the simple you get much higher values than with Biot particle finder. And then what they did also is the manual reassessment of the data, and they removed spectra which were not really fitting well. And then you get something which is much more similar here. The concentrations are much more similar now. And you can see that in general, the trend is quite good if you compare these both methods. But for individual sites, it might still be that there are quite some differences. For example, here, sample 3 is here is nearly nothing, and here you have quite a lot. That means also there, for individual samples, there's still quite a bias. And this is only the data analysis. There's nothing before, it's not extraction, it's not sampling, it's all the same, it's just data analysis, which you might still implement quite some issues. On another paper which was also published this year, so you see that people are now focusing more on this issue. This is a complete comparison of 2 different methods. One is quite a sophisticated method, also water analysis, from Aalborg University, where they do also enzymes and oxidations, and they have quite a sophisticated machine with a multi-element detector. And when they analyze the same samples, then they get something like between 420 and 2,500 particles per cubic meter of water in this case. And below there's quite an easy method, which was established by a commercial lab, and this is just a very basic density separation, oxidation, and less sophisticated method. And then you see exactly the same sample, you can see that they get something between 17 and 17 microplastics per cubic meter. So there's a factor of about 30 in between in the concentrations. So, and this is of course the whole sequence. So the sampling is not included, so it was the same sample, but the whole extraction and measurement, data evaluation thing. But it's also for water. Yeah, and soil is sometimes even more complicated. So when we come to the conclusion, we can say that, of course, microplastic analysis is still challenging. We heard a lot about it already, and I think we will talk about it also later during this conference still. Yeah, you can see that there's quite a potential for errors in different steps, but I think at the moment, really, I think there was quite some publications about this, and there's quite a lot of discussion about these extraction steps, which should be homogenized with the same density separation and things like that. I think it's really about a lot about the data evaluation, which you have to take care of. And you can say that you cannot compare values from the literature. It's just too different. And I really think that if you do a lot of effort, you can generate values which are quite good or in a certain range. But when you look on all the papers which are published also from older times, then there was much less awareness about this kind of issues, and the values might be really not comparable to what we find to date. Yeah. And there's not always this, we need standardization, it's always said, and I totally agree on that, but first I think we have to know about which method to really choose to standardize, because they're quite different still, and it's quite hard to figure out what is the best method to use. I mean, there are very good methods, but they need a very high effort, and there are other methods which are performing faster, but maybe the results are not so good. So this needs to be discussed. This is. I thank you for listening to me.
Thank you, Moritz, for the very interesting keynotes. There are questions from the audience. So.
Thanks for the talk. Just a quick question as a microbiologist. Do you think that surface changes due to biofilm or fungal growth is an issue for you in the encouragement of microplastic into a complex environment? It's not an issue.
Yeah, it can be. It depends a bit on the method. I mean, if you do this digestion of the organic matter, then I would assume that you also digest a lot of the biofilms. So then it would not be that much of an issue, but I don't know if this is really investigated by now. It really depends. I think if you have a well-working method where you oxidize organic matter, then you might also oxidize the biofilm.
Thank you. You showed one slide where you presented different results from different devices. Was it possible in that study to transfer the same filter from one device to the other, or are those actually different samples on different filters? Because I think for the ADR you need a different filter than for the FTR in transmission mode, right? So
the one, our study,
where you did the single point, FTR, the Raman, and the LDR. So could you use the same filter, or was it on multiple filters, and did you have to send it around to different labs? How did you do that?
Yeah. So this is really a different extraction and different analysis. Yeah. So of course the FPA and the MCT detector, you can measure it on the same filter, but for the LDR, this is deposition on the central holder, which is reflective, so it's another method. So but the extraction procedure and everything, the handling before, it was homogenized. It was the same, but it still, of course, contribute to the error. I mean, what we see at the moment is just that the differences I presented there is just, I think, quite a lot from the data evaluation.
Thank you for the presentation. I just have a general question regarding that. That's true in each step that you presented. There are a lot of be biased. For example, when we separate, we consider the particles as an inert material there, but in fact they interact with the soil and then with the organic matter. Then you have a huge cluster of particles within organic material that you cannot separate them with these methods. And then you selectively select, I mean not you, in general, the literature, selectively select some particle and represent to all, while the hardest particle, which probably considered the most particle there, they are ignored. So, and for example, regarding the question that the microbiome, definitely microbiome will change it, and the method that you are using today, probably after microbiome, like functionalizing the particles, then it doesn't work after 2 weeks, the same method, because of the activity of microbiome. So, considering all these, what do you think the way forward in this field of sample preparation?
Yeah, I mean, what you see just is that now the studies are starting to compare the methods, and I think this is a big step forward now. I think, as I said, for the extraction, we are quite good. I think there are methods which are working. I mean, there would be more or less just finding one common method, and also for the sampling in principle, we know what to do. And I think now all the steps just have to be put together to get something which is comparable. And yes, as I said, I think at the moment there's still quite some effort in the data analysis which need to be taken. Also, I mean, I just showed a few examples here, but you also have, for example, you take the spectral measure and you have to compare to a library, and then the question is, how's the library? What spectra are in there? This also affects, of course, the results you get at the end. So we really have to think about these individual steps and do it the best way. And I think when we start now to comparing the method, we are getting closer to it.
Thank you. The last question.
The next one is Martha Elisabetta Church. We try to